Hello, I'm Dr. Alison Griffiths of Staffs University. Today I'm going to talk about Arduino port manipulation. The purpose of this is so that we can turn our general purpose input-output pins on and off more rapidly than using Arduino libraries. So we'll start off with a pinout of the Atmega 328 chip, which can be found on the boards, the Arduino boards. In pink, we can see the Arduino IDE pins that we're used to referencing. So 0 here is digital pin 0 up to digital pin 13. Then we've got the analog pins, which can also be referenced as digital pin 14 or up to 19. So the analog pins are shown in green, and they also have analog to digital converters on them. But for output, they can be used as digital pins if they're not being used as input. The other pins can be used for other functions, which we can see the PC interrupts, for example. We've got crystals and oscillators. Some of the digital pins are pulse width modulated and can be used for counters and timers. This can be covered in another session. What we're looking at today are the boxes that are next to the actual pins on the chip. So the yellow boxes or the port pins. Now we can see that in the port pins we have a port, a letter, and then a number. There are 3 ports. Port B. So port B is 8 bits, and it refers to digital pin 8. So digital pin 8 to 13. So it's 8 bits, so it has 1, 2, 3, 4. 1, 2, 3, 4 bits. Now we can refer to this as a binary number, a hexadecimal number, or even a decimal number. It's best to stick to either binary or hexadecimal. Now, when we're first teaching or learning how to manipulate the ports, binary is the easiest. And then once we understand the ports, we can convert these numbers to hexadecimal, and it's more of a shorthand way of doing things. The actual chip itself is not bothered whether the number is binary, hexadecimal, or decimal. We can tell the Arduino in our programming by using a OX for hexadecimal and a B for binary, the format of the number. It then converts it to machine code anyway for us. So port D is also 8 bits, and it refers to pin 0, digital pin 0 to digital pin 7. Port C is 7 bits, and this refers to the analog input pins or digital output pins. It's 7 bits, but the 7th bit, or PC, port C, bit 6, doesn't have a general purpose input output pin, GPIO, general purpose input output pin. It doesn't have a pin associated with it because that's the reset pin. So let's look at the very simple program of the blink program. Now, usually we have delays in here so that we can visually see an LED going on and off, turning on and off. However, the purpose of this program is to see how fast the pin can go high to low, or 5 volts to 0 volts. So in program 1, we've used Arduino commands like pin mode and digital write. In program 2, we have used the data direction register, or the DDR, and that can either be B, C, or D, depending on which port that we are referring to. And then we are inside our void loop. So the void loop takes time to execute. If we use a while one, we never come out of this loop, whereas in the first program, we loop round using the void loop. The purpose of using the while one loop is that it's faster. I will talk about these operations and this operation a little bit more in the next few slides. But the purpose of this slide is to show that when we use program 1, then the frequency of the on-off period is found as 1, 2, 3 squares here. And the scale is 100 microseconds, meaning each square is 10 microseconds. So we've got 3 times 10 microseconds, and if we do 1 over that, the frequency of the waveform or the on-off period, the maximum performance that we can get out of our Arduino is 33.3 kilohertz. However, this is in Tinkercad. The link is found here for you to do this yourself and check it. But if we use real hardware, it's found to have been up to 121 kilohertz. So Tinkercad is good for the development environment. However, we get much better performance in real hardware. On this second code, code 2, we do exactly the same thing. I shall explain this is turning the Arduino pin 13 on, and this is turning it off. So if we take the period of this waveform, it's just over 4 squares, and it's 0.3 microseconds per square. So the time period is 4.1 times 0.3 microseconds, and if we say 1 over that, it comes to approximately 800 kilohertz. That would be for 4. It's 813 for 4.1. So if we round that up to 0.8 megahertz, whereas again, in comparison with real hardware, we get 2.66 megahertz. I would encourage you to try this in the lab with a real oscilloscope. Now, obviously, the more instructions that you add to this program, then you're not going to get the same frequency out. But this is to show the maximum frequency that we can achieve with an Arduino. So now I'm going to explain line by line the program, or the program line by line. So first of all, what does this OX20 mean and 001? We need to know where this number comes from. I've got an excerpt of the diagram here that I showed in previous slides. So pin 13 is port B, bit 5. So what do I mean by that? So port B, this is bit 0. This would be bit 4, bit 3 even. This is bit 7, bit 4. This is bit 5. So if I only want to turn on pin 13 and not turn on. If I want to refer to pin 13, first of all, I want to refer to pin 13. So I want this bit to be high. So I want this bit to be a 1. So we can either, in our program, write data direction register. So the data direction register means, of port B, means if it's a 0, it's an input. If it's a 1, it's an output. So we just want pin 13 to be an output. So we need to set this as a 1. So all of these bits we want to be 0, and this bit 5, we want to be a 1. So we can set it like this. So data direction register equals data direction register, or, so what's already in the data direction register, we OR it with binary 00100001. So that would be zeros in all the other bits and just a 1 in port B, bit 5. We could also write it in hexadecimal. So we could convert this number to hexadecimal. So in converting binary to hexadecimal and the other way around, then if we take 4 bits, then we have the first bit being 2 to the power of 0, which equals 1, then 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So we've got 1, 2, 4, 8. So those are all set to 0, so that's our 0. Then the second bit, because it's 8-bit, is 2 to the 0 is 0, 2 to the 1 is a 1. So here we have a 2. So in hexadecimal, 20 equals 0, 0, 1, 0, 0, 0, 0, 0. If we OR this with the contents of port B already, what that's going to do is make sure that this bit is going to be a 1 and the other bits in the other ports will remain as they are. I shall show this in lines 12 and 13, which are on the next slide. So now we want to switch that pin, so pin 13, to be high. So we're going to do an OR with port B with hexadecimal 20 or binary 20, 0, 0, 0, or this value 0, 0, 0, 0, 1, 0, 0. I've just shown this as in red to show that it is pin 13 and that is bit 5 of our number, which also equates to hexadecimal 20. So let's say that we have port B and some of the values, some of the bits in it are already 1. So here we've got a 1, here we've got a 1, and here we've got a 1. Now, bit 5 could either have a 0 or 1 in it already. So if we OR the contents with what's already in port B with 20 hex or this, then the resultant is 0 exclusive, not exclusively odd, apologise. 0 ORed with 0 gives 0. Again, 0 ORed with 0 gives 0. 0 ORed with 1 gives 1. Again, 0, again 1. Now, here, regardless, if there's a 0 here, then 1 ORed with 0 will give a 1. And 1 ORed with 1 will also give a 1. So we will always get a 1 in the desired bit. So bit 5 will always be 1 after this operation. And the other bits will remain. So the other bits of port B are unchanged. Okay, so this is really important that we notice that the other bits are unchanged. And this one is, we'll always get a 1. In the same vein, then if we take lines 15 and 16 in the program, and that means port B and equals not, and I'll write OX 20. So, and the contents of port B with the not of hexadecimal 20. So we worked out before that the value in binary of 20 is this. So the not of 20 in hexadecimal is 110 11111. Now we're ANDing it with the contents of port B. So what that means is whatever is in these bits, or these bits of port B, they will stay as they were, and whatever is in bit 5 will go low to 0, because if we're ANDing anything with a 0, whether it's a 0 or whether it was a 1, the resultant will be a 0. So we have the contents, which are the same as they were before. So we AND 1 and a 0, and we get a 0. And 1 and a 0, that's the same, we get a 0. 1 and a 1, we still get 1. 1 and a 0, we get a 0. 0 and 0 is 0. So if this, we now come on to bit 5. If we had a 1 in port B, so in our program it is going to be a 1. So if we had a 1 in port in bit 5, then the resultant of 0 and 1 is going to be a 0. If it happened to be that that bit was 0, 0 and 0 is still going to give a 0. So this will be off. And we AND 1 and 1, that'll still give us a 1. 1 and 1 will give us a 1. So these are exactly the same. Second line and the bottom line are still the same, whereas we've made sure that bit 5 is off. Now, the good thing about this is that we can apply the same rules if we wish to turn multiple bits on and off. Sorry, multiple pins on and off. So for example, here I've got another 1. So if we do binary 0, 0, 1, 0, 1, 0, 0, 0, 1, 2, 3, 4. So that would be bit 3, and this is still bit 5. So this in hexadecimal would be 2, and this would be 2 to the 0, 2 to 1, 2 to 2, and 2 to 3. So this would be O hex 28. So instead of 20 there, that would be O hex 28 for the equivalent code. So then that would be make this pin output. So this pin would be pin 13, 14, that would be pin 12, data pin 12 off the IDE. Sorry, the pin 13, 11, that would be pin 11 off memory. So we would have pin 13 and pin 11 going high and low. I can take you to my Tinkercad to show this in operation. In fact, I have pin 13, pin 11 in this one. This is the file. And I've also got another LED connected to digital pin 2. And if I look at my diagram, digital pin 2, I go to PowerPoint. Digital pin 2 is connected to port D bit 2. So port D bit 0, 1, 2 is set to 1. This is also given an output on 0 there. That's not port B, that is port D. So I'm now turning on and off port D and B. So port B here, turn on, port D on. And if I run this simulation, I can see that I am actually getting the same frequency on both ports. I can stop that simulation, and I've got different configurations of switching the ports on and off. So if I put, for example, these two pins on and off on port B, then on and off again, then port D, I can say on, on, on. So I can manually create a pulse width modulated signal if I wanted to. So I can create different waveforms. I may want to zoom out on the scope. So if I double click, I can say, rather than 0.5, I'll zoom out to 1 microsecond. So now I can see that I am on for 1.8 cycles, and then I am off for longer too. These are 1.8 there, and then 2.56 cycles. Again, I can zoom in and measure this. And if you used hardware, you could use a scope, a proper scope with measurements so that you could measure the actual on and off time. Just investigating the speed that we can get out of this method. So start the simulation and go back to my PowerPoint and go to the slide. So my Question is, can you write a program to facilitate this result? What ports are required? Which bits in those ports are required to switch on and off?